Okay, so welcome you all to this tutorial session. Please feel free to ask any doubts from the assignment problem or from the lecture notes that you might have. Yeah.
Hello, sir.
Yeah.
Sir, I have a doubt on question number three, sir.
What is the doubt?
Uh, Sir, I can't solve the problem.
Okay, so let us see that. Problem number 3 you're saying, right?
Yes, sir.
You can see the assignment sheet, right?
Yes, sir.
So you see, in your BSc, you did a central limit theorem for only one random variable, right? Single random variable, that means random variable in the real life, right?
Yes, sir.
So x1, x2, xn are IID, normal mu sigma square. Sorry, x1, x2, xn are IID with mean mu and finite variance sigma square. Then root n x bar minus mu goes in distribution to normal 0 sigma square, right? Based on this, you did a delta method, which says that if root n delta n minus g theta goes in distribution to z, right? Then root n times g times delta n minus g of theta would go in distribution to g prime z, g prime theta z, where I assume that g prime theta is not zero, because if theta g prime theta is zero, then g prime theta z is zero, so you'll get a convergence in probability, right? So that is the result. Now, similar generalization holds for the multivariate case. So there is a concept of a multivariate central limit theorem. So it is the same thing, except that now here what happens is you take the mean component wise, right? So y1, y2, yn, then y bar 1, y bar 2, y bar n, normalize it with root n minus whatever is the mean of y bar 1, y bar 2, y bar n will go in distribution to normal 0 sigma star. And this sigma star are determined through the variances and covariances which occur in the sample mean, right, of the three components, right? That is what it says. And then you can apply the delta method also over here, except that now here g may be the g function which you are applying may not be a univariate. It may be a from Rn to Rm, right? Even g may take values as a vector, right? So here, in that case, except for that g prime, it will come as a matrix of a Hessian matrix, right? Partial derivative of partial derivatives, right? That is what it will come. Right? So that is the whole concept. Now, if that is the case, then what you need to do over here is you need to prove the central limit theorem for S1 square, S2 square, S12 square. So somehow you should be in a position to write down S1 square, S2 square, and S12 as mean of something, right? As a mean of something. The only problem I see over here is mean of IIDs, I should be able to do that. The only problem I see over here is xi minus x bar whole square is there. If xi minus mu whole square was there, there was no problem. It was a mean of xi minus mu whole square, right? If it is in place of summation yi minus y bar whole square, it was 1 upon n summation yi minus mu whole square. No problem, because then it was a mean of yi minus mu whole squares. Right? Now note that this is also a mean, but it is a mean of yi minus y bar whole square, which we are not IID, right? Because of the same factor y bar. But if you put yi minus mu whole square, then mu is common, it is a constant, and yi's are IID, so yi minus mu whole square would be IID. So that is the whole purpose. Similarly, when I look at S12, this x bar and y bar will not make it IID. But if I make it xi minus mu and yi minus mu, then xi minus mu and yi minus mu's are IID, because x1, y1 and x2, y2 are independent. So x1 minus mu, mu1 y1 minus mu1 and x2 minus mu2 and y2 minus mu2 would be IID. So in this case also, if I put here mu1 and here mu2, then I get IID. So it looks like first I should apply the central limit theorem only with means. When I have a mu1 over here, when I have a mu2 over here mu1, here mu2. And then I should convert this quantity into xi minus mu1 whole square, as we did in the problem number 1, right? As we did in the problem number 1 yesterday, because it was 1 upon n summation xi minus x bar whole square. So first I prove the central limit theorem for 1 upon n summation xi minus mu whole square, and then we did it. So exactly that is what we do. We'll do it. So I can get a asymptotic distribution of this. Once I have asymptotic distribution of this, R I can get through applying G on this, right? G would be nothing but Z upon square root of xy. So I can get the distribution of root n of G of this, right? So that is the whole concept. So let us try to do it step by step. So note that first I define Ti1s, which are xi minus mu1 whole square, because then Ti1s would be IID. Ti2 is yi minus mu1 whole square. Yi minus mu2 it should be actually. Ti2 should be yi minus mu2 whole square. And Ti3 is xi minus mu1 and yi minus mu2. T bar 1 has 1 upon n Ti1, mean of this one. T bar 2 is mean of Ti2s. And T bar 3 as mean of the IC, so that I can apply central limit theorem of all this, provided Ti's are IID. Ti is nothing but Ti1, Ti2, Ti3. Note that Ti1 only depends on the ith vector, right? Because this is xi, this is the second component of ith vector, and this is the product of cross product of the ith components, right? And xi's are IID. Since xi, if you vary i's, these xi's are IID. So as you vary I, these Ti's are IID, right? So that means I can apply the central limit theorem to Ti's. No problem with that. The only thing I need to know is what are their means, because that normalizing factor will depend on what are the means of Ti's. And that variance covariance matrix would be the variance covariance matrix of this vector Ti, because they are IID. So I need to determine its mean and its variance. So let us try to do that. So T bar vector I have known as T bar 1, T bar 2, T bar 3. So theta 1, which is the first vector, which is expected value of Ti1. Expected value of Ti1 is nothing but expected value of xi minus mu1 whole square, which is nothing but sigma 1 square. Is that okay? I look at what is the mean of the second vector, theta 2, which is Ti2. Expected value of Ti2 is nothing but expected value of yi minus mu2 whole square, which is nothing but sigma 2 square. Right? Theta 3, which is expected value of Ti3. Expected value of Ti3 is nothing but expected value of xi minus mu1 into yi minus mu2. So this is nothing but covariance between xi and yi, which is nothing but correlation between xi and yi. Standard deviation of xi is to standard deviation of, right? So that is, so I have got the mean vector theta 1, theta 2, theta 3. So I know that this T bar has to be subtracted with theta 1, theta 2, theta 3. Now I look at the variance covariance matrix. So first I look at the first diagonal element in the variance covariance matrix, which will be nothing but variance of Ti1, which is nothing but variance of xi minus mu1 whole square. What is the variance of xi minus mu1 whole square? It is expected value of xi minus mu1 whole 4, right? Minus expected value of xi minus mu square whole square, right? Which is expected Ti square minus expected Ti1 whole square. But expected value of xi minus mu1 whole 4 is related to kurtosis, which is nothing but gamma 1 times sigma 1 to power 4. Is that okay? Minus expected value of square of this, which is nothing but sigma 1 to power 4. So minus sigma 1 to power 4. So the first diagonal element is nothing but gamma 1 minus 1 sigma 1 to power 4. Is that okay?
Yes, sir.
What is the second diagonal element? By the same logic, it relates to yi's. It would be nothing but gamma 2 minus 1 sigma 2 to power 4, where gamma 2 is the kurtosis of yi's. Is that okay? What is sigma 3,3, which is nothing but variance of this quantity? which is nothing but variance of x1 minus mu1, y1 minus mu2, which is nothing but expected value of x1 minus mu1 whole square, y1 minus mu2 whole square, minus expected value of this whole square. But expected value of this is nothing but covariance between x1 and y1, which is nothing but rho sigma 1 sigma 2, so square of that. So rho square sigma 1 square sigma 2 square. Right? So this is what turns out to be the third diagonal element. Now I look at the covariance terms. Sigma 1 2 square is covariance between T11 and T12, which is the very covariance with expected value of x1 minus mu1 whole square, y1 minus mu2 whole square into expected value of x1 minus mu1 whole square, which is sigma 1 square, into expected value of y1 minus mu2 whole square, which is sigma 2 square. So this will be sigma 2 square. Sigma 1 3 star is nothing but covariance between T11 and T13, which is expected value of x1 minus mu1 into x1 minus mu1 into y1 minus mu2. Sorry, expected value of x1 minus mu1 whole square. So basically this into this. So that means x1 minus mu1 whole cube into y1 minus mu2. Minus expected value of T11, which is nothing but sigma 1 square. And expected value of T1 is nothing but rho sigma 1 sigma 2. So this becomes rho times sigma 1 cube sigma 2. Similarly, sigma 2 3 is covariance between T12, T13 by the same logic. It becomes x1 minus mu1, y1 minus mu2 whole cube. This would be whole cube minus rho sigma 1 sigma 2. Right? So we have got the covariance matrix. Here gamma 1 is the kurtosis of x1, gamma 2 is kurtosis of x2. Let us look at theta as theta 1, theta 2, theta 3, sigma star as the matrix sigma star. So what I get by the central limit theorem? Root n, the mean vector, minus the corresponding mean theta 1, theta 2, theta 3 goes in distribution to R, which is like what normal 0 sigma star. And sigma star terms are given by this. Right? Is that okay? Is that clear? Any doubt up to
Yes,
this?
sir. No, sir. No doubt.
Now the only thing I need to do is I need to convert. I wanted to get a central limit theorem for S1 square, S2 square, and S12. So somehow I have to convert these into S1 square, S2 square, and S12. So when I look at root n times S1 minus sigma 1 square, I can convert summation xi minus x bar whole square. I can add mu1 and subtract mu2 as I did in the first problem. Then it becomes root n times t1 bar minus sigma 1 square minus root n times x bar minus mu1 whole square. Similarly, root n s2 square minus sigma 2 square is equal to root n t2 bar minus sigma 2 square whole square minus root n y bar 2 minus mu2 whole square. And root n s12 minus gamma sigma 12, I add in xi mu1 and subtract mu1, yi I add this thing, so this becomes root n t3 bar minus this would be rho, not nu, rho sigma 1. So rho sigma 1 sigma 2 minus root n x bar minus mu1 and y bar minus mu2, right? Standard thing. So what do you get? Root n s1 square s2 square minus sigma 2 square into root n s sigma 1 square sigma 2 square rho sigma 1 sigma 2 is nothing but root n t bar 1 t bar 2 t bar 3, and these are theta 1 theta 2 theta 3, right? So that is theta 1 theta 2 theta 3 minus root n, the second term, x bar minus mu1 whole square, y bar minus mu2 whole square, x bar minus mu1, y bar minus mu2. Is that okay? Now I try to look at where does this goes to. Right. Now I know that root n x bar minus mu1 goes in distribution to normal, right? So time, that means n times root n x bar minus mu1 will go to normal 0 1 square. Similarly, this will go to normal 0 2 whole square, and this would go to something, right? So what does that mean? Here I am only getting root n. Root n can be written as n upon root n, right? Root n can be written as n upon root n. But I know that n times x bar minus mu1 whole square goes to something. And 1 upon root n, so it will go to 0. Each component wise, they go in probability to 0. Is that okay?
Yes, sir.
Because root n x bar minus mu1 goes in distribution to normal 0 1. Is that okay?
Yes, sir.
When I write down this as, root 10 x bar minus mu 1 times, and then x bar minus mu 1. I can write down this as root 10 x bar minus mu 1 into x bar minus mu 1. Root 10 x bar minus mu 1 goes in distribution to something, and x bar minus mu 1 goes in probability to 0. Right? By law of large number. So the product will go in probability to 0. So each component wise they go in probability to 0. If each component wise they go in probability to 0, jointly they go in probability to 0, right? Because that is what we did in the lecture. If you have to show a vector goes in probability to 0, try to show that each component goes in probability to 0. So that means this goes in probability to 0. If this goes in probability to 0 and this goes in distribution to multivariate normal, this whole thing will go in distribution to multivariate normal by Stratsky's lemma. So that means root 10 s1 square s2 square s1 2 minus sigma 1 square sigma 2 square rho sigma 1 2 goes in distribution to r1 r2 r3, which is normal 0 sigma star. Is that okay? Any issues so far?
No, sir.
Now you have to find a distribution of a correlation, right? Correlation, you can get a function of this. How can you get a function of this? This is s12 divided by square root of s1 square root of s2 square. This says that I should apply function hxyz on this with hxyz given by the third component z, which is s12, divided by square root of first component square root of second component. So this says that I should consider function this, and then I can apply the delta method on this, right? But this is a function of 3 variables. In one variable you only needed one derivative. Now here it is a since function of a 3 variable, you need a derivative with respect to all the 3 components, partial derivatives. So first I do, so this I did in the notes, right? That you can see delta method, multivariate delta method in the notes. So partial derivative with respect to x of this quantity becomes minus z upon twice x root xy. Partial derivative of this with respect to y becomes minus z upon twice y root xy. Partial derivative of this with respect to z becomes 1 upon square root xy. Is that okay? So what I get, since this was going in distribution to this, by delta method root 10 times h of this, what is h of this? s12 upon s1 and 2. Minus h of this, what is h of this? Third component divided by square root of the first and 2, which is the rho. Rho sigma 1 sigma 2 by sigma 1 sigma 2. Goes in distribution to the vector of partial derivative of this at the point sigma 1 square, sigma 2 square, and rho sigma 1 sigma 2. Right? What is this value at this point? Z is rho sigma 1 sigma 2 and sigma 1 sigma 2. So minus rho sigma 1 sigma 2 twice first component sigma 1 square into square root of sigma 1 sigma 2, square root of xy. So which is square root of this. Derivative of this at this point, theta, which is nothing but z minus rho sigma 1 sigma 2, 2y, that means 2 times sigma 2 square, then square root of xy, which is square root of sigma 1 square sigma 2 square, which is sigma 1 sigma 2, into derivative with respect to third component at this point, which is 1 upon square root xy. Square root xy is square root of sigma 1 square sigma 2 square, which is 1 upon sigma 1 sigma 2 into r1 r2 r3. Right? That is what the delta method says. In the case of 1, there was only one variable, h prime theta. Here it would be a vector of partial derivatives. And then wherever convergence was going, r1, r2, r3. So these r1, r2, r3. So I do this. This becomes minus rho twice sigma 1 square r1 minus rho times twice sigma 2 square r2 plus r3 by sigma 1 sigma 2. r1, r2, r3 is a multivariate normal. R1, R2, R3 is a multivariate normal. So all its linear combinations are univariate normal. Is that okay? That is the definition of a multivariate normal distribution. A random vector has a multivariate normal distribution if and only if all its linear combinations have a univariate normal distribution. And it is a linear combination of univariate normal. Linear combination of components of a multivariate normal, so it will have a univariate normal. Once it is univariate normal, I know its mean. Its mean I can find out expect loop R1, expect loop R2 into expect loop R3, right? Which has a mean 0, so mean would be 0. What would be the variance? Variance you can calculate rho square by twice sigma 1 square variance of R1 plus rho square. So that you can see is same as tau square, where tau square is given by this quantity. Right? Tau square is a variance of this. Now you know variances of Ri's and covariances of Ri's. So you can determine what variance of this quantity would be. Because you know the variance covariance matrix of R1, R2, R3. So this is going to be this quantity, you can calculate it. So I have got the distribution of asymptotic distribution of correlation coefficient. Now in the case of normal distribution, let Z1 is x1 minus mu1 and Z2 is x2 minus mu2 by sigma 2. Then Z1, Z2 has a bivariate normal with mean at 0, 0 and variance as 1 rho and rho 1. So I'm trying to now see what would be this quantity in the case of a bivariate normal distribution. Then sigma 1, 1 star is gamma 1, 1 minus sigma 1 to power 4. For normal distribution, because x1 is normal, but if Z1 would be normal because bivariate normal, so marginals are normal. So its kurtosis is 3. So 3 minus 1 sigma 1 to power 4, which is 2 sigma 1 to power 4. Similarly, sigma 2, 2 star would be gamma 2 minus 1 sigma 2 to power 4, which is 3 minus 1, 2 sigma 2 to power 4. Sigma 3, 3 star would be expected of x1 minus mu1 whole square, y2 minus mu2 whole square, minus rho square, sigma 1 square, sigma 2 square, which is nothing but this quantity becomes Z1 square, Z2 square into sigma 1 square, sigma 2 square. So sigma 1 square, sigma 2 square becomes common. Expected value of Z1 square, Z2 square minus rho square. So what you need to find out is expected value of Z1 square, Z2 square minus rho square when Z1, Z2 has a bivariate normal, right? So you can use the conditional expectation. So expected value of Z1 square, Z2 square is same as expected value of Z1 square, Z2 square given Z1, which is same as expected value of Z1 square into expected value of Z2 square given Z1. To find expected value of Z2 square given Z1, you need to know the conditional distribution of Z2 given Z1. Z1, Z2 is bivariate normal. In the bivariate normal, what is the conditional distribution? Anyone?
It's also a univariate normal.
So you can find the distribution of Z2 given Z1, which will be a univariate normal. And then you can find out expected value of Z2 square, which is variance plus expected value of Z2, Z1 whole square. So these are variance of Z2 given Z1. And this is the expected value of Z2 given Z1. That you can find out from the conditional distribution. So it turns out to be 1 plus 2 rho square. So sigma 3, 3 star turns out to be 1 plus 2 rho square minus rho square is 1 plus rho square into sigma 1 square, sigma 2 square. Similarly, sigma 1, 2 square is same as equivalent of x1 minus mu1 whole square, y1 minus mu2 whole square, which is sigma 1 square, sigma 2 square, equivalent of z1 square, z2 square minus 1, which is 2 rho square, sigma 1 square, sigma 2 square. Right? Same, you can find it, equivalent of z1 square, z2 square, we have found it out. 1 plus 2 rho square. So 1, 1 gets cancelled, so 2 rho square, sigma 1 square, sigma 2 square. What would be sigma 1, 3 star? We have seen before, expected of x1 minus mu1 whole cube, y1 minus mu2 minus rho sigma 1 cube, sigma 2. This is z1 cube, z2 and sigma 1 cube, sigma 2. So sigma 1 cube, sigma 2, z1 cube, z2 minus 2. So I again find out what is expected of z1 cube, z2, which is expected value of z1 cube given z2, which is expected of z1 cube given z2 given z1. Expected of z2 given z1 I know is same as rho z1. So which becomes rho times expected z1 to power 4. Z1 is univariate normal, 0, 1, so it is 3. It is kurtosis because variance is 1, so it is 3 rho. So sigma 1, 3 star, I put the value over here, I get as this. Similarly, I can find sigma 2, 3 star, which is this quantity minus rho, and this turns out to be this quantity. So then I can put all these values in tau square. So tau square, if you put those values, you get 1 minus rho square, whole square. So what do you get? In the case of bivariate normal, everything simplifies quite a bit. And what you get is root n r minus rho. Root n r minus rho goes in distribution to normal 0 tau square. And tau square is this quantity. which you have found out is 1 minus rho square whole square. So now you get root n r minus rho goes in distribution place. Now what you have to do is, you see, normally what happens is you try to get an asymptotic distribution so that your variance does not depend on a parameter, right? Because that helps. That is called a variance stabilizing transformation. You might be doing it in simulations or all that, right? Because that helps. If your approximation is such that it depends on rho, then there is a lot of volatility in the approximation. So you would like to get an approximation which does not depend on rho. So if you take that, so that means I should try to get a transformation on R so that this does not depend on rho. So I consider hx to be half times log of 1 plus x upon 1 minus x, which is half. And then I apply delta method on h. Then what I get? Root n times h of r. H of r is nothing but half times log of 1 plus r upon 1 minus r minus h of rho. H of rho is nothing but half log of 1 plus rho upon 1 minus rho, goes in distribution to h prime rho times z. H prime rho is nothing but 1 minus rho square into z. But 1 minus rho square into z is nothing but normal 0. Z is normal 0, 1 minus rho square, so it is normal 0. So this is what this is. The purpose of this was to apply the variance stabilizing transformation so that asymptotic distribution does not involve any parameter. That is the one advantage. Is that okay? So that proves. So the idea is
Sir,
that everything is based on a central limit theorem for multivariate distributions and the delta method for multivariate normal distribution. So this is a nice application where you can learn multivariate central limit theorem and how to apply delta method in the multivariate setting. Yes, any doubts so far? Yeah.
No, sir.
how will you know that before that this transformation will use us independent of theta distribution,
That you must be doing it.
independent of some parameter?
That you must be doing in your simulation course. Now, you see, you need a transformation. Finally, what happens? I have to apply a transformation H over here.
Hmm.
If I apply a transformation H over here, what distribution I get? Root n HR minus H rho will go in distribution to H prime rho.
Hmm.
But H prime rho times Z will have a distribution normal 0 H prime rho whole square into 1 minus rho square whole square.
Okay, I got it.
Right? Now you want H prime rho whole square into 1 minus rho square whole square should be a constant.
Hmm.
Right? And that is how you get this transformation. Is that okay?
Yes.
Is that okay? Yeah.
Sir, can you
That is called a variance stabilizing constant because you see, whatever approximation you use, because rho may be unknown to you, you would not like to use an approximation which is very volatile to choice of rho. For example, if rho is near 1 or rho square is near 1, this is almost degenerate distribution. Right? You would like to absorb all that volatility in the left-hand side itself so that the volatility in the approximation doesn't come. Is that okay? That is the whole idea. Yeah. Anything else?
sir, can you please once again show that sigma 1 3 calculation of sigma 1 3? Why is it sigma cube?
Where
Sir,
sigma 1 3 star.
yes, sir, sigma 1. Yes, sir. This.
So let us look at sigma 1 3 star is the first component and the third component, right? Let me see. Yeah. First component is this and third component is this. Right? So x1 minus mu1 whole square into x1 minus mu1 into y1 minus mu2. Which is nothing but expected value of x1 minus mu1 whole cube into y1 minus mu2. So that is expected value of ti1 into ti3 minus expected value of this, which is sigma 1 square into expected value of ti3, which is nothing but rho sigma 1 sigma 2.
Oh, okay, sir. Okay, sir.
Is that okay?
Yes, sir.
Because it is x1 minus mu1 whole square into x1 minus mu1. That is how cube will come. Because when you take the covariance between this and this, expected value of this into this, expected value of this into this means x1 minus mu1 whole square into x1 minus mu1 into y1 minus mu. That is how the cube is coming. Does that clarify?
Yes, sir. Yes.
Okay. So I would say that this is a very nice exercise, which is very simple. Calculations are simple, but it gives you the whole idea about using the multivariate central limit theorem, using the multivariate delta method, because all other courses you might have seen, you must have used delta method very frequently. But very few places you use delta method in the multivariate setup. Now, this is a very, very nice application. Now, if you even when you do the next course, which is multivariate analysis, you would see that asymptotic distribution of correlation is obtained over there. Now, here you see very nice proof of that is given over here. Is it okay? Now, note that this can be used to get an asymptotic confidence interval for log of 1 plus rho upon 1 minus rho. Is that okay? Because this is normal 0, 1. It does not depend on theta. So that means probability that this quantity lies between minus z alpha by 2 to z alpha by 2 is 1 minus alpha. And you can convert this into log of 1 plus rho upon 1 minus rho or 1 plus rho upon 1 minus rho. What kind of function 1 plus rho upon 1 minus rho is? It will be a monotone function. So from here, you can get a confidence interval for rho. Because any statement upon 1 plus rho upon 1 minus rho, because it is a monotone function of rho, can be converted into a statement about rho. So this asymptotic approximation can also be used to get confidence intervals for rho. Because this thing does not depend on rho, and you can find probability that this lies between minus alpha by 2 to alpha by 2 is 1 minus alpha. And left hand side, you can convert this statement into 1 plus rho lying upon 1 minus rho lying between two ranges is 1 minus alpha by 2. And then that's all. Yes, any other doubt you have?
Sir, can you show the answer of 2? I just want to check that if it is.
Answer of 2.
Yes, sir.
Problem number 2. So this is the thing, gamma plus 3 upon 4 sigma square plus beta by sigma, where beta is... so this is again similar to this thing. This is a much simpler form of problem number 3.
Yes, sir.
Right? Because you have to get a distribution of root of n x bar minus mu and s1 square minus sigma square. Right? So x bar is a mean, but s1 square is not a mean, so I consider x1 minus xi minus mu whole square. Right? Then I know that y1, y2 are IID. What is a mean vector? Mean of xi, which is mu. Mean of xi minus mu whole square is sigma square. What is a covariance matrix? Covariance between, so the first component is variance of x1, which is sigma 1 square. Variance of the second component, which is variance of x1 minus mu whole square, which we have seen is gamma minus 1 sigma to power 4 many times, right? It is expect of x1 minus mu to power whole 4 minus expect of this whole square. Expect this whole square is sigma 1 to power 4. So minus sigma 1 to power 4. And expect of x1 minus mu to power whole 4 is nothing but kurtosis times sigma 1 to power 4. Is that okay?
Yes, sir.
And what is the covariance term? Covariance is expect of x1 into x1 minus mu whole square, which can be written as x1 minus mu into x1 minus mu whole square minus sigma square, which is expect of x1 minus mu whole cube, which is beta, which is basically the skewness. Is that okay?
Yes.
Because x1 minus mu with sigma square would become 0. Is that okay?
Yes, sir.
So this is what it turns out to be. So root n y bar minus theta goes in distribution to normal 0 sigma, where sigma is this, where beta is the skewness. So I apply now Vn as x bar n minus mu and Rn as root n upon n summation xi minus mu whole square sigma square. So Vn upon Rn goes in distribution to this. The usual technique, right? I convert x bar minus mu s square minus c sigma square into that. And then you get us this. Is that okay?
Yes, sir. Yes, sir.
And now you can apply the transformation because you want the distribution of x bar plus s. So that means the first component plus square root of second. So hxy is x plus root y. root n h of that quantity minus h of this goes in distribution to, again, you have to get a two partial derivatives with respect to x, which is 1, with respect to y, which is 1 upon 2 root y, 1 upon 2 root y at sigma square is equal to 1 upon 2 sigma VR, and this is what you get. Is that okay? So exactly same as problem 3. It is much easier because here you are using only multivariate central limit theorem in R2. The problem number 3 use the multivariate central limit theorem in R3. Right? Is that okay?
Yes, sir.
Okay. Any other doubt?
But sir, this part is not in the assignment that you uploaded. That the plus part.
I think you see, I have modified, I have now uploaded a modified version. Just see the latest version of the assignment.
Oh, okay, sir.
Right?
There is also a typo in problem number 3.
There may be. So what I'm saying is just see the latest version. Just
Oh, okay,
latest,
sir.
right?
Yes, sir.
I uploaded it 3 days back, 2-3 days back, the modified version. Right? Is that okay?
Oh, I didn't check that actually.
Just check that all of you see the latest version of the assignment.
Okay, sir.
Yes, any other doubt anybody has?
Sir, in problem number 4, I did the first part, and after that,
Problem number 4. Right.
yes, sir. Yeah, I did the first part, and that is okay. Then after that, should I, when I have to show that n by n plus 1 x order n is consistent estimator, then using the previous fact, previous result, should I do that, or
Yeah, you can
I
use
should?
that because once you have shown that n theta minus xn goes in distribution to z, then theta minus xn would be nothing but 1 upon n into n times theta minus xn. N minus
Yes, sir.
theta xn goes to z and 1 upon n goes to 0.
Yes, sir. Yes.
That means theta minus xn will go in probability to 0 by Stratsky's lemma.
Yes, sir.
It is equivalent to saying that xn goes in probability to theta. Xn goes in probability to theta and n upon n plus 1 goes to 1. Then you know that if Cn goes to C and Xn goes to X in probability, then Cn Xn will go to Cx. So that is why this will go to theta. Is that okay?
Yes, yes, sir. Means in spite of using that fact, I calculating the expectation of x order n and variance of x order n. So in limiting sense, expectation of x order n goes to theta,
Right.
and the variance goes to 0. And you proved a theorem that if xn is consistent for theta,
Right.
and if limit n tends to infinity, an tends to 1, then an xn is also consistent for theta.
Right. So you can use it. The only thing is here, if you look at problem, I have showed that first you show that, and using this you show that it is consistent. So your solution is correct if you have to just show it. But what I'm saying is you have to show it using that n theta minus xn goes in distribution to z.
Okay, sir. Okay. Okay.
It says hence so that. Hence so that.
Yes, sir.
If it was hence or otherwise so that, then your second solution would have been acceptable. Your solution is correct. There is no problem with the solution. But here what is being asked is using this you so that. Is that okay?
Okay, sir. Okay.
Any other doubt?
Sir, in problem number 6, how to proceed for the consistent estimator, means there is any hint.
Okay. So note that, let us see if you have to approach this problem, how should I do it? These are some function of theta. I know a consistent estimator of theta. What is a consistent estimator of theta? Can you give me one consistent estimator of theta?
X bar.
X bar. So X bar is consistent.
Hmm.
So that means if G is continuous, then G of X bar would be continuous for consistent for G of theta by a result which we did in the class.
Hmm.
Right? The only thing here is this G is not continuous. It is continuous except at one point, theta is equal to 0.
Equal to 0.
Right. So let us put G of x bar, what it would be. G of x bar would be x bar if G of x bar would be 0 if x bar is not equal to 0, and 1 if x bar is equal to 0. So, but probability x bar is equal to 0 is 0. So G of x bar is essentially 0. That is what you are saying. Right? If you directly apply x bar. But that is happening because of a continuous distribution. Ideally, it should have been my of G of x bar is 0 if x bar is not 0, and 1 if x bar is equal to 0. So what I do is I slightly modify this, because this estimator as it is 0, because probability x bar is equal to 0 is 0. So this will never occur. So it will always be this. But it says G of x bar is 0, 1 if x bar is 0. I modify it and say that, no, if x bar is not 0, if x bar is near 0, I make it 1. Right? So it looks like a modified estimator could be, my estimator is 1 if x bar is near 0 and 0 otherwise. X bar is near 0 means mod of x bar is less than an, kind of a thing, and 0 otherwise. So my intuition suggests a estimator which would be 1 near 0 and 0 otherwise. That is the estimator I should try, right? And that is what the problem number 6. Yeah, so this is what it is saying. So I put Kn, that means if mod of x bar is less than Kn, that means x bar is in the neighborhood of 0, I make it 1 and 0 otherwise. And then I suitably try to play around with this Kn so that my x bar becomes consistent. Right? And that is what I have done over here. I consider first case theta is equal to 0 and then case theta not equal to 0. You can do this, right? There is no doubt in this. Right? You can work out with algebra. Right? How do we get this estimator? That motivation I have told you. Okay. So now you have to only show that this is consistent for theta. So you have to consider two cases, theta not equal to 0. Theta not equal to 0, I consider mod of delta n x minus g theta greater than or equal to epsilon. I try to show that this goes to 0 for every epsilon greater than 0. But when theta is 0, my g theta is 0. So, g theta is 1. So this is same as probability that mod of delta n x minus 1 is greater than or equal to epsilon. Delta n x depends on what my x bar is. So I apply theorem of total probability. First, in the case one mod of x bar is greater than or equal to kn, but if mod of x bar is greater than or equal to kn, delta n is 0. So this is same as probability 1 is greater than or equal to epsilon, plus mod of x bar less than kn. When x bar is less than kn, my delta n is 1. So 1 minus 1 is 0. So 0 greater than or equal to epsilon. But since my epsilon is always greater than 0, this probability would always be 0. Right? Probability would always be 0. So that means if epsilon is between, so only this event will come. Now this event also would be positive only when epsilon is less than or equal to 1. So epsilon greater than 1, even this is 0. So this becomes 0 if epsilon greater than 1. If epsilon is between 0 to 1, this is always satisfied. So the only thing which you will be left with, probability mod of x bar is greater than or equal to kn, which is same as 1 minus probability that x bar lies between minus kn to kn, which can be written as, because theta is 0, mean is 0, so it is phi root n kn minus phi minus root kn, which can be written as 2 times 1 minus phi of root n kn, 0, if it's between 0 to 1. So I need to show that this should go to 0, right? Now this would go to 0 if root n kn goes to infinity, right? So this goes to 0 provided root n kn goes to infinity. I should choose kn so that root n kn goes to infinity. But I have to consider second case also. In second case also, I should get consistent, theta not equal to 0. Probability mod of delta n x minus g theta greater than or equal to epsilon, which is same as, for theta not equal to 0, g theta is 0. So this is same as probability mod of delta n x is greater than or equal to epsilon. I again break, according to theorem of total probability, mod of x bar n greater than or equal to epsilon. In this case, this would be kn, right? Mod of x bar n greater than or equal to, so this is this. This turns out to be this. So he says, suppose kn goes to 0 and root n kn goes to infinity, then everything goes to 0. So that is what you get. And Kn you can get a choice as Kn, for example, n to power minus 1 by 4 would do, right? For this, Kn goes to 0 and this. So this is that okay? So you have got a consistent estimator. Yeah. Any other doubts? Yes. Does anybody has any other doubt? Yes. Anybody? Don't seem to have any doubts. Let's see. So 1, 2, 3 we have done. 4 is straightforward. 5 you might have done in your estimation course also. How do you do 5? Anyone? So note that TXIs are mean. Right?
Sir, I did it, sir, using some regularity conditions using because EX is sufficient.
Yeah, because this is exponential, so all those regularity conditions are satisfied, right? Now this is a mean. So if you can show that expected value of Tx1 is psi prime theta, because Tx1, Tx2, Txn are IID. It is a mean. So if it is a mean, psi prime theta is expected value of Tx1 and psi double prime theta is a variance of Tx1, you have proved it, right? So the only thing you need to show is expected value of Tx1 is psi prime theta and variance of Tx1 is psi double prime theta.
Yes, sir. Means if I integrate the PDF,
Right.
that is equals to 1.
Very nice.
So
and then you can differentiate it both the sides.
yes, sir. With respect to theta, then
exactly the same thing. So and then you are able to do it, right?
yes, sir.
You are able to get expected value of Tx1 as psi prime theta and variance of Tx1 as psi double prime theta, right?
Yes, sir.
Yeah, that is what you have to prove. That is what you have to prove. 6 we have done just now. What about the 7th one?
The first part is done, sir.
Okay. X bar may not be consistent. How do you prove that?
Sir, I wrote the multivariate distribution. Then I calculate the distribution of X bar. Then I show that it is not convergent in probability to 0.
So what you can do is you can consider. So what it says is when these xi's are correlated, there could be a problem. When they are independent, you know that X bar goes in probability to theta, right?
Yes, sir.
So what it says is in dependence case, there could be a problem. So what you do is simplest thing is because multivariate is the easiest thing to handle. So you take suppose x1, x2, xn have a multivariate normal distribution for every finite n. And with mean as theta, 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 same mean. Each component has the same mean. And correlation matrix as, let us say, 1, 1, 1 and correlation as rho j, same correlation, right? So if you do that, this is a problem number. Yeah, so this is x1, x2, xn has a normal mu, 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 sigma, right? Basically, it says for every n, my x1, x2, xn sequence is such that for every n, x1, x2, xn is this, because n is varying. Where sigma ij is, correlations are variances are same, and they have a same correlation rho as it is given in part 1. So what I have to show? I have to show that x bar is not consistent. So I consider probability mod of x bar minus mu is less than epsilon. What will be the distribution of x bar in this case? Again normal, with mean as mu, variance as sigma square by n plus n minus 1 by n rho, right? X bar, because x bar is a linear combination of x1, x2, xn. So if x1, x2, xn has a multivariate normal, x bar would have a univariate normal, being a linear combination of x1, x2, xn. Now, once I know that it is a univariate normal, the only thing I need to know is what are its parameters, its mean and variance. What is the mean of x bar? X proof x1 plus x proof x2 plus x proof xn by n, so n mu upon n, which is mu. What will be the variance of x bar? Sigma square by n plus 2 times summation I not equal to j, covariance of xi and xj. Covariance of xi and xj is nothing but rho times, this is what it comes, sigma 1, sigma square should also come because I have taken a sigma square, right, n minus 1 upon n.
Covariance are given as rho.
Covariance is given as
Rho, sir.
Right.
Yes, sir. Yes.
so then that is okay. So covariance is, so this is the, so I convert this as x bar lies between mu minus sigma to mu plus sigma and so on. So it becomes phi of root n sigma. So you normalize just by this quantity, root n sigma by square root of sigma square plus this, minus root n sigma by sigma. Where does this goes to as n goes to infinity? This will go to sigma upon rho. This will go to minus sigma upon rho because root n is coming from here, which is 2 times phi of sigma by root rho minus 1. So if rho is not equal to 0, this is not equal to 1. So this will not be consistent. Now second part, when x bar is bounded, then you know that expected value of x bar is mu. So if you can show that variance of x bar goes to 0, you are done, right? In the second part. So I try to look at variance of x bar, which is sigma square by n, twice time n square, summation I not equal to j, or which is same as 2 times summation I less than j, right? So it is 2 times n square, summation I less than j is summation j is equal to I plus 1 to n, I is equal to 1 to n minus 1. For j is equal to I plus 1, correlation is nothing but r to power j minus I. I put it over there, I sum it out, this turns out to be this. Sum it out, and this goes to 0 as n goes to infinity. So x bar converges in probability to mu. Is that okay? So I just put, I find out it's less than or equal to this, and then I calculate, this is a geometric series, I can calculate this, and then everything turns out to be very nice. Because n square is coming over here, so this will go to 0. This will also go to 0. This will also go to 0. So everything goes to 0. And since r is less than 1, n minus 1 will always go to 0. Is that okay?
Yes, sir.
Okay.
So what you would see is now let us look at problem number 8. I think that we did last time. It is same as these are counter example to show that if your convergence in probability does not imply expected value delta n minus mu whole square will go to 0. Okay? That you can do. Uniform case, you have to show this quantity. Is that okay?
Yes, sir.
Now note that here you cannot use the formula which we did in the class because that was based on h of x bar. Is that okay? So here you have to make it just based on h of t, which is maximum of x1, x2, x. Apply the Taylor series theorem on h of t. H of t would be same as h of theta plus t minus theta, h prime theta plus t minus theta whole square by factorial to h double prime theta. And then h4 something you try to show the way you did exactly for x bar, exactly you did over here, except that you know that t would have a PD of n to power t to power n minus 1 by theta to power n. So you can calculate various things. Right? So try to do these problems. We still have a one session tomorrow, right? So we'll discuss those. Rest of the problems are not that difficult, except that this I think we did in the class. There is slight typos over there. In place of x bar, you have to consider the mean of u naught minus xi, right? Ti as u naught minus xi in this problem, problem number 12. So let me stop over here, and we'll again meet tomorrow and try to do in between the problems. Rest of the problems is ARE, other things are simpler problems. You can just let us again meet tomorrow, and let us try to discuss the remaining problems. Is that okay?
Yes, sir.
Okay,
Yes, sir.
Thank you,
Okay.
sir.
Okay,
Thank you,
bye.
sir.
Bye for today.
Thank you, sir.
Okay. So we'll meet tomorrow.
Hmm.